Hello everyone, and welcome to the video on verifying trig identities. Now what verifying means is that instead of given a trig expression, you're given a trig equation like this one down here in green, and you're trying to verify or prove that this side equals this side. And the question a lot of students ask is say like, wow, the teachers are just going to give me the answers. Well, that is very true. What an identity really is it's saying that this side has to equal this side. In fact, this is an identity. Sine squared x plus cosine squared x equals 1. That you're saying one side must equal the other. And here's how you go about proving these identities. You need to start with one side and prove that the other side is equal. So what we could do is start with this side and try to manipulate that to get here, or we could start this side and manipulate it to get here. Never are you going to do both sides at the same time because you need to make sure that one is the same as the other. So in terms of rules and strategies, number one is most important. Choose one side, usually the left, I would say. A lot of students usually start with the left side, but it could be whichever one you'd like to work with, and do not touch the other side. Because if you touch both sides, you're not really proving the identity. You need to completely manipulate one side to equal the other. And some of these strategies you're going to recognize from the last couple videos. Like the last videos, when we simplified trig expressions, we substituted identities we saw first. That's usually the first thing we thought about. Then if those didn't work, we used some of the algebraic skills. We factored, we distributed, we combined fractions with a common denominator, we split the fractions from one fraction to two, or two fractions back to one. And something that's good about this particular unit is if we go back to this example, what this means, note which trig functions are in the final expression. So if we looked back at this example, we have cotangent and tangent. You'd have to ask yourself, what can I do to get secant and cosecant? Or if you started with this, what could I do to get cotangent and tangent? A couple other things we can do is use a conjugate. And just like last video, when all else fails, change from sine to cosine. The best way to learn these is to do them. So let's get started. Here's an identity. Secant of y times cosine of y equals 1. So the side that I would definitely start with is the left side, because there's a lot of ways you can write 1, and it seems to be endless, so I'd rather start with something more concrete. So if I write secant of y times cosine of y equals 1, we need to manipulate this side so we can prove 1. So what I notice is that secant, as a reciprocal, can be written as 1 over cosine of y. And now this we are just going to leave as cosine of y, because if I have a cosine on the top and the bottom, they cross out. And this is technically over 1. So I'm left with 1 over 1 equals 1. So I get that this side equals this side, and you can put a big check mark. Now, this is what we're going to be looking for on a future test or quiz. You need to show us that this side never changed and remained 1, and this side became 1, and the check mark in some way means that you're done with the identity or proved it. You also could make a little box. That's another way to say that you have proven the identity. Let's take a look at this one. If I had to start between the two sides, I would yet again start with the left side because there's more to do to get to cosine. So let's think about this. Remember, we're not touching this side at all. So if we look at just this side, what could we possibly do? Well, first let's see if there's an identity we can replace. We want just cosine. As this said, remember, if all else fails, change to sine and cosine. So if you don't see anything else you can do on here, you can take tangent and change that to be the identity sine over cosine. So this sine of b is going to stay the same, but this tangent is going to become sine of b over cosine of b, based on the identities we've used in the last two videos. So let's think about reciprocals or dividing fractions here. If I think in numbers first, if I have 4 divided by 2/3, that's really the same as 4 divided by 2/3 written differently, which is really 4 times the reciprocal 3/2. So if I use that logic here, this is the same as sine of beta divided by sine of beta over cosine of beta, which is the same as sine of beta times the reciprocal of cosine of beta over sine of beta. Now, lucky for us, I noticed that we have these signs cross out, so I'm just left with cosine of b on this side. And if we carry down the cosine of b every time, we get that the identity is verified. We got that this side is cosine of b or beta, and this is cosine of beta also. So check, I've proven or verified the identity. Some of you may be asking yourself, how did Mrs. Logos know to do that? Well, again, it comes from practice, like anything else, like a sport, a musical instrument. You need to practice it to know enough relationships here. I knew that if I have a sine on top and I knew that tangent changed to sine over cosine, that my sines would eventually cancel out. So kind of a good gut instinct, but again, the more you practice, the better you're going to get. Speaking of practice, let's keep going. Oh, this one looks like a doozy. Let's see what we can do here. So we want to verify this identity. We want to get this mess to somehow become secant to the fifth and tangent to the third. My suggestion would be, again, starting with this left side because it's a lot more complicated. So let's see. I noticed that we do have secant tangent in common, so we could take out a GCF, but just to make this a little bit less complicated, let's just distribute in the secant to the fourth and the secant to the sixth. Now there's no plus sign in either one of these, so what you're really doing is just multiplying this in. So this is going to become, if I'm doing secant to the sixth times secant, there's 7 of them, so it'd be secant to the 7th x, and the tangent just comes along for the ride because it's attached, minus secant, and this is really secant to the first, so that's 5 secants, and then tangent again just comes along for the ride. We want to make sure that this side eventually equals this. So I'm going to carry this all the way down. If I look back at this side, again, I am not touching this side at all. I'm just manipulating this side. Here's where factoring can help us, specifically a greatest common factor. When I look at this term and this term, I notice that I can take out 5 secants and I can take out a single tangent from both terms. So I'm going to take out secant to the fifth and a tangent x, and when I do that, I'm left with, so if I take secant of 7 divided by secant of 5, I'm left with 2 of them, and if I take a tangent out of a tangent, that's gone, minus. If I take 5 secants out of 5, that's gone or divides to be 1, and if I take a tangent divided by tangent, that's also divides to be 1, so I'm left with just 1 here, and that should still equal this. All right, let's see if there's anything else I can do with this side. I notice that I have a squared function here, and that squared secant makes me think of the Pythagorean identities. So let me go back to the first notes that we did. Here is a secant squared. I know that tangent squared theta plus 1 equals secant squared theta. So let me write that back over here on the top. I know that tangent squared of x plus 1 equals secant squared of x. So if I want to get secant squared minus 1 on the same side, I would subtract the 1 over, and I would get that tangent squared of x equals secant squared minus 1. So all of this can just be replaced with tangent squared x. And I still have the secant to the fifth, and I have the tangent of x here, and I hope that I'm getting closer to this untouched side. Good news, I have 1 tangent here and 2 here. That means that I have tangent to the third or 3 tangents, and I have secant to the fifth. I now have that this side equals this side exactly. So check, I have verified the identity. So greatest common factors are extremely useful sometimes. So when in doubt, take it out. Here's another one to verify. My suggestion again, common is the left side, not always though. We want to try to get this side to become secant of x. So let's see what we can do. Cosine is being added and it's all by its lonesome, so I'm going to leave that first because there's nothing I can do to that yet. But this one, again, as a gut instinct, I know that tangent is sine over cosine. So let me change it to that so we can get everything in terms of sines and cosines at least to start. We want to try to get it to be secant of x. Now, in terms of the algebra skills, I noticed that I couldn't get a common denominator. I couldn't factor anything out. There's no GCF here. There's no fractions I can combine. So that's why I relied on changing things to sines and cosines. So if I keep simplifying, this, I have two signs on the top. So that becomes sine squared x over cosine of x. I want to try that to be secant of x. Now it looks like I might be stuck until I realize that this cosine of x is really over 1. And remember, one strategy algebraically is to find a common denominator. Sometimes it may help. So let's try it here. The common denominator between 1 and cosine of x is going to be cosine of x. So that means that this first fraction needs to be multiplied top and bottom by cosine of x. And if I do that, I would get cosine squared x over cosine plus sine squared x over cosine, and that should equal secant of x. Now that I have two fractions with the same denominator, I can write it as one fraction. I know that cosine squared x plus sine squared x all over cosine should hopefully equal secant of x. And at this point, I hope that some of you are going, aha, sine squared theta plus cosine squared theta, or x, is 1. So this is an identity and can be replaced with just 1 over cosine of x. Does that equal secant of x? Well, are cosine and secant reciprocals? Yes, they are. 1 over cosine is the same thing as secant, and so I get that both sides equal secant of x. So check, I have verified the identity. These Pythagoreans, quite useful, I have to say. This next one, based on what we just did with common denominators, I would like you to try on your own first. My suggestion, you can go either direction, but I would suggest starting on this left side and think about eventually getting a common denominator after you do a particular substitution of an identity. So please pause the video now and try this one on your own, and I will come back with the answer. Please pause now. Okay, so let me check in with you so far. The first thing I did was I changed secant to be 1 over cosine. Then I noticed that because this was over 1, I could get a common denominator. So I multiplied the second fraction by cosine over cosine, and that became 1 over cosine minus cosine squared over cosine. Once these had the same denominator, I combined it into one fraction, and the top became 1 minus cosine squared of x. That made me think, because it was squared, of the Pythagorean identity, sine squared plus cosine squared equals 1. If I subtracted the cosine over, I got that sine squared equals exactly this. So I replaced 1 minus cosine squared with sine squared over cosine, and that's where I stopped so far. So please pause the video now if you would like to copy any of this down. I'm very close. I got rid of my subtraction sign, so that's a good news. The question is, how do I get here? Well, let's think about, what does sine squared mean? It really means sine times sine. So if I really have two sines on top and I have a single cosine on the bottom, that means that I have a sine of x, and then sine over cosine is really defined as tangent. So I have both sides now equaling sine x times tangent x. Verified. Now this is one that is tough. There's a lot going on here, but this is one that I would definitely consider going back and trying again on your own, because not only does it have identities, it has getting a common denominator, combining fractions, and then an identity again. So there's a lot to it. Now the next example, again, I will do on another video. I'm capped at 15 minutes. So instead of rushing, I would like to briefly do the next example, and there's one we're going to do in class together. So please pause now and join me on the next video. Thank you.